Hi everyone, in today's lesson we're going to talk about a concept called related rates. Related rates is a real-world application to implicit differentiation. So the best way I can do this is through a couple of examples. So let's start with example number 1. It says, the radius of a spherical balloon is increasing at a rate of 3 feet per minute. How fast is the volume increasing when the radius is 2 feet? So the first thing we need to do is decode the words, all right? So when it says the radius is increasing at a rate of 3 feet per minute. Every time you see rate, I want you to think derivative. And the reason why we think derivative when it comes to rate is because derivative means slope of a tangent line, which means slope means rate of change. So rate, change in distance over time. And then it's asking here, how fast is the volume increasing? So how fast is also a rate, or how slow. So this is also a rate, which is also a derivative. So let's write out what we have. So the radius of a spherical balloon is increasing at a rate of 3 feet per minute. So you see we have a distance and then we have a time, right? Feet per minute. So the way we write the rate would be dr dt. The rate at which the radius, dr dt, the rate with respect to time, is increasing at a rate of 3 feet per minute. And then they want to know how fast is the volume. So they're saying volume this time. So volume, we can use the letter V. So we can say dV dt. And we're going to put a question mark. How fast is the volume increasing when the radius is exactly 2 feet? So our R is 2. So now that we're able to decode this, we need to use a formula. So we're talking about a spherical balloon and we're talking about its volume. So I'm giving you the formula for a volume of a sphere. So we're going to start by writing it down. Volume equals 4/3 pi r cubed. Now, in order to plug in dr dt or dv dt, since these are derivatives, we have to take the derivative of both sides of the equation. So the derivative of v is simply dv dt. And the derivative of this right side, 4/3 and pi are simply a constant. So we're just going to take the derivative of r to the third. So you want to kind of think of it like this. Here's an example. So say I had 5r to the third. The derivative would be 15r squared. If I had 5 pi r to the third, you would still do the same thing. 5 times 3 is 15. You just tack on the pi. So 15 pi r squared. So we're going to do the same thing here. We're going to multiply the 3 times 4/3. So 3 times 4/3 pi r squared. But since I took the derivative with respect to r, we need a dr dt. So if you notice, this is similar to implicit differentiation. But the only difference is that we need to put, you know how we had a dy dx only when it was dy dx when it was respect to y? We need a dv dt and a dr dt. We need it every single time we take the derivative with any letter. Okay, so now let's plug in. So dv dt is what we need to solve for. So I'm actually going to leave that as dv dt. And when we multiply this 3 times 4/3, these will cancel. So we're really left with 4 pi r. Do I have an r? Yes, I do. R is 2, so I'm going to plug in 2 squared. And dr dt we absolutely have. That's 3. So the answer to this question is basically what this comes out to. So we're going to say dv dt equals, I can do this math in my head. 2 squared is 4. 4 times 4 is 16. 16 times 3 is 48. So we can tack on the pi and just call it 48 pi. And since we're talking about volume, we need to remember the units for volume. Volume is cubic. So since we have feet, it would be feet cubed per minute. So again, volume is cubic meters or cubic feet. We have area, which we know is square meters or square feet. So that will just help you with your units. Okay, let's take a look at example number 2. Example number 2, an oil spills from a tanker and it spreads out in a circular pattern centered around the tanker's position. If the perimeter of the spill, so we can say perimeter of the spill, is moving outwards at 2 meters per second, find the rate of increase of the contaminated area when the radius is exactly 500 meters. So you should see there's two things happening. They're talking about perimeter and they're talking about area. So you might have two formulas. The first example only had one. So let's write down what we know and then we can figure out what we need. So if the perimeter of the spill is moving outward at a rate of 2 meters per second. Now, perimeter of a circle. Let's actually even draw a picture of this. Oil is spilling from a tanker. So let's just say like here's the truck bed, right? Here are the wheels. It's lifted down. Oil is spilling out on the floor and it's creating a circular pattern. So the first drop is really small. Then it gets bigger and bigger and bigger and bigger and bigger. So the spill is just getting bigger in this circular pattern. So perimeter, we can say, is the same as circumference when I'm talking about a circle, right? Perimeter is this outside, so we call that circumference. I'm just abbreviating. And area would be all the stuff inside of the circle. So perimeter, is spilling out at a rate. It doesn't say rate, but it says meters per second. So meters per second is our rate. So dc, I could say for circumference, dc dt, the derivative of the circumference with respect to time is increasing at a rate of 2 meters per second. It says find the rate of increase of the contaminated area. So I want to find the rate at which the area is increasing. That's dA dt. I can say the area is increasing with respect to time. So find this when the radius, r, is exactly 500 meters. Right? So all I did was pull out the information and write it here. So the thing that I'm going to start with is the fact that they ask us to find this, find the rate of the increase of the contaminated area. So I'm going to start with my area formula for a circle. Area equals pi r squared. So I need to find dA dt, so let's take the derivative of all the sides. So A is dA dt, and the derivative of pi r squared, take the 2, bring it in front, leave the pi, r, decrease the power by 1, so 2 minus 1 is 1. And since I took the derivative with respect to r, I need a dr dt. So dA dt will be found by taking 2 times pi times my r, my radius, which is 500. And then I just need to plug in my dr dt. Now the problem is I don't have dr dt, right? They only gave us this information. We used this piece and this piece, but we didn't use this yet, dc dt, the rate at which the perimeter or circumference is changing. So why don't we now use this formula to help us out? So over here, I'm just going to write circumference equals 2 pi r, and I'm going to take the derivative. So dc dt. And then the derivative of 2 pi r, that's the same thing as taking the derivative, say, an example of 5r. The derivative of 5r is just 5, just the number in front. So the derivative of 2 pi r is just 2 pi. And then I take dr dt, right? Because I took the derivative with respect to r. So since I have dc dt, the change in circumference is 2, I can put that here. And then 2 pi and dr dt. So to solve for dr dt, I'm just going to divide both sides by 2 pi. And the 2's can cancel, so we're just left with 1 over pi. Now, it's in your best interest to leave it in this form and not make it a decimal, because watch, bottom pi with top pi can cancel. So my dA dt is 2 times 500, which is 1,000. So 1,000, but now we're talking about area, so we need the right units. So since it's meters, we would write meters squared per second. Volume was cubed, meters is squared. Okay, that's my second example. Okay, I see here that I have examples on the back, but I'd like to actually end this video. You can leave those 2 questions blank, and we will start class by going over those 2 tomorrow in class. All right, have a good night. So it says the top of a 10-foot ladder is sliding down a wall at a rate of 3 feet per second.